We said before with the aromatic chemistry, forming carbon-carbon bonds is really important because that's where you can start to increase the size of your drug molecule, for example. You can introduce additional complexity by being able to form carbon-carbon bonds. So can we use carbon as a nucleophile? And the answer is yes. One example is to use the cyano group. So if you take an aldehyde or a ketone with HCN, so hydrogen cyanide, it gives you a cyanohydrin. So if you have this kind of hydrogen cyanide, a cyanide is a nucleophile, under specific conditions, this exists in equilibrium and it exists as Cn minus, with the minus on the carbon. Okay? So normally though, that HCN is actually too weak to provide a protein for the acid catalyzed reaction. Okay, so although it's slightly acidic, it's not acidic enough. So that means we follow the basic reaction mechanism. So we can say we have Cn minus. Okay, we have our carbonyl. And we're just going to do that basic mechanism where we say we have a charged nucleophile, an uncharged carbonyl. So we're going to react the nucleophile with the delta positive carbon. It's now got too many bonds, so we're going to break the carbon-oxygen double bond. Okay, that's exactly the same thing we've done before. Then we're going to use some kind of proton from somewhere. That can come from water, but in this case it could come from the hydrogen cyanide as well. And we end up adding so we've made a carbon-carbon bond. Now, we're not going to go on to show that you can take that cyano group and you can do more chemistry on that to create other functional groups. So you could turn that into an amide, for example, or you could turn it into an amine. But it just shows you can form those carbon-carbon bonds. Obviously, hopefully, you guys would have reckoned that hydrogen cyanide is fairly toxic, so it's not something that we really want to be using in the lab that often. And what we would usually do is use something like a sodium or potassium cyanide with a bit of acid in there is the one that we would usually use. So we wouldn't add hydrogen cyanide because obviously we can poison ourselves or the other people in our lab, so we prefer to use something a little bit safer, so we'd use something like a potassium or sodium. So if you see potassium cyanide plus acid, you can know that that means you've got a source of Cn minus again. Okay. And that's why, as I said, a lot of this chemistry is not about the carbonyl. The carbonyl is the same all the time. It's how you get your nucleophile. It's how you get your electrophile that's the important thing. So that's an example of how we can add a cyanide, and that's a relatively straightforward one because it is just the Cn minus charged nucleophile onto an uncharged carbonyl. But we want to sometimes make more than just adding a cyano group. If we want to form a proper carbon-carbon bond, we want to add an extra alkyl chain, for example. How do we do that? Well, we can use something that's called a Grignard reagent. So the Grignard reagent gives us a source of carbanions, so C minus. So we're not going to worry too much about how you make Grignard reagents. All we need to know is that a Grignard reagent is this one here, where you have your carbon, the R group, attached to magnesium with a bromine there as well. And again, what we're saying is if you see a Grignard reagent, you can say, well, that technically equals R minus. You can do the same with an aromatic group as well to give you an AR minus. Okay? But what it means is you've got a source of a charged carbon nucleophile. So it gives you that nucleophilic carbon group. Okay. So if we've got a nucleophilic carbon group, we have a nucleophile and it's charged, therefore we can react it with our carbonyl. So again, you can either write, Grignard reagent equals R minus, or we can show how it can be if you put the R Mg Br. Okay. What we're saying effectively is that the electrons in that bond predominantly reside on the carbon, which is what gives it its negative charge. So you can use those electrons as if they belong to your carbon, and you can do that reaction. So you can take both electrons out of that bond, break the bond between the carbon and the magnesium, and react it with the carbonyl carbon. And once you've done that, you then need to, as we've done countless times already, break the carbon-oxygen double bond. And again, it's just worth noting that the magnesium at this point would get a positive charge on it because it's lost its electrons. Your oxygen has a negative charge, so they form a kind of a salt. Just temporarily in the reaction mixture, the magnesium bromide will associate with the negative charge on the oxygen. But all you need to do is add a bit of acid, which will be taken up by that negative charge. And again, what you then end up with is another alcohol. And you can imagine that if you start with a ketone, or so if you start with an aldehyde, you'd end up with a secondary alcohol. If you start with a ketone, you'll end up with a tertiary alcohol. Because at the moment, we're not worried about what's attached to here, but you can imagine if they were, one of them was a hydrogen, one of them was a carbon, you've got a secondary alcohol. If they were both carbons, you'd have a tertiary alcohol. So doing this Grignard reagent is a really nice way of creating, you're changing your carbonyl to an alcohol, but you're adding this R group to it. And of course that R group could have lots of other stuff in it. It might not just be an alkyl chain, it could be more than that. But for most of what we'll show you, they would be carbon chains. We'd be using things like, methyl magnesium bromide or ethyl magnesium bromide. And then the last one is that we can also add what's called an alkyne or an acetylide. So if you have this kind of alkyne, so a triple bonded, carbon triple bonded to carbon, again, if you add at this time a strong base, that will give you a source of C minus again. And as we said, if we get a source of C minus, that can act as our nucleophile. And again, it's an example of a charged nucleophile, which means it's just our standard base catalyzed reaction that would be, you take your thing, you've got C minus, that attacks the carbonyl carbon, which is electron deficient. We then break the carbon oxygen double bond. You get your O minus, add a proton, and there you've added your triple bond across. So those last ones, they are all just saying to you, the reaction mechanism in each one of those steps is the same. It's just that you've got to remind yourself or remember how you're generating your charged nucleophile. Are you doing it from a cyano group? Are you doing it from a Grignard reagent? Or are you doing it from a triple bond? So to get it with a cyano group, you need to have a little bit of acid, you need to deprotonate the cyano group so that you get C minus. For the Grignard reagent, it's a Grignard reagent itself which gives the R minus, and for this one you need to add a base to it to remove this proton, which will then give you a C minus. Okay, so those are the bits that you might need to learn and remember, But once you've got that charged nucleophile, you're following the same reaction mechanism from then on. Okay? So, with the last 5 minutes, let's see if we can do a reaction with a Grignard reagent. Okay, so remember that methyl magnesium bromide, it's a Grignard. You've got some acid in there, so you can follow that. Generate your charged nucleophile. Think about how that would work. React it with a carbonyl to get your product.